Hey YouTube, and welcome to Tech Talks. We are back again for another question. We're solving 75 questions in 75 days from the famous Blind 75 challenge. We're still tackling the binary questions, and this is the third one in that section. It's question 338 called Counting Bits, and the question asks us this. Given an integer n, return an array of length n plus 1 such that for each index in the array is the number of ones in the binary representation of the iterator. So let's look at some examples to see exactly what this means. Example 1, they give us n as 2 and we want to return 0, 1 and 1. And that is because counting from 0 to 2, we have 0 ones in 0, we have 1 bits in 1, and we have 1 bits in 2. Let's take a look at a larger example. In example 2, we have n equals 5, and the output is 0, 1, 1, 2, 1, 2. And the reason for that, again, we went through the first 3 indexes in this array. 0 would be 0 1 bits, 1 would be 1 bits, 2 would be 1 bits, 3 would be 2 1 bits, 4 would be 1 bits, and 5 would be 2 1 bits. So hopefully that starts to make sense. So to solve this in a kind of naive way, we can just take our algorithm that we worked out yesterday for counting how many 1 bits are in a given integer, and then we can just iterate from 0 to n, completing that algorithm for each iteration. Let's take a quick look at what that gives us. So we just want to define an integer array. And that's just going to be of size n plus 1 because we want to take care of n and we also want to account for 0. And next we just want to iterate from 0 to n. So we'll do int I equals 0 while I is less than or equal to n. And we'll just increment each time we pass through. And now let's insert our algorithm from yesterday. So we're going to do int num equals to I and int total number of ones equal to 0 for now. And then we'll do while num is not equal to 0. And we want to check if num and 1, so we're checking for the bit in the lowest position, is not equal to 0, meaning we've got a 1. We just want to increment the total. And then we just bit shift num down. So we're just going to do num equals num, and we're going to bit shift 1 place. And when we've looped through all of that and num now equals to 0, we just want to place the result at I equal to that total. And finally, let's return the results array. And let's go ahead and run that. Great, so our answer's been accepted, but this is kind of inefficient. So if we just analyze our algorithm for a second, we're executing this code block once for every iteration up to n. And the highlighted code block actually has a runtime of log of n. So our entire algorithm is big O of n log n. And funnily enough, if we scroll down, we actually have a follow-up question. And it says, it's very easy to come up with a solution with a runtime of big O of n log n. Can you do it in linear time, that's big O of n, and possibly in one single pass? Well, it turns out we actually can, and all it takes is a little backtracing to see what's stored in previous positions. Let's just go ahead and remove this O of log of n algorithm, and I'll show you what I mean. So I've gone ahead and written out the binary representation for all the integers from 0 to 8. Let's imagine for a second that we're already iterating from 0 to n, and we're now at I equals 4. So we've computed 0, 1, 2, 3, and we're now looking at 4. Let's think for a second, what's the difference between 4 and the rest of the numbers that we've already iterated through? Well, of course, they have a 1 in this position. So that just goes to show that we already know how many 1 bits are in the iterations before we reach 4. So then how can we make 4 equal something that we've already seen? So all we really need to do is modify the bits in 4 and then just look back at what we stored for that representation. So what we can actually do is just bit shift one place. Let's make this equal to 0010, and that of course equals to 2. So let's take a look at how many ones we stored when we stored 2, and of course we would have stored 1 bit for that iteration. So that means we can just say we have 1 known bit, but if we look back at the binary representation of 4, all we're really doing is checking these first 3 bits that I've listed out. And then what distinguishes 4 from 5? Well, it of course is that last bit. And if you didn't already know, the last bit will be 0 if the number is even, or 1 if the number is odd. So to figure out if that number is odd or even, all we need to do is AND it with 1. So in this case, we'll just do I, which equals to 4, and we'll AND it with 1, and of course we will come out with 0. Let's take a look at another example. Let's go ahead and use 7. So we'll just bit shift. We're going to do 0011, and let's look back at that iteration. So that of course is 3, and we'll look at how many we would have stored for 3, which would have been 2. So we know that we have 2 known bits. And then let's just add 7 and 1. And of course, we're looking at that last bit, and we'll come out with a 0001 because those 2 bits are the same. And that of course will be 2 bits plus 1 bit, which equals 3. And our algorithm will just continue on and on and on, always looking back at what was previously stored and then checking whether the number is odd or even until we finally reach n. Let's go ahead and clean that up, and let's get started with the implementation. So all we want to do is we are iterating through our for loop is say that results at I is equal to results at I bit shifted one place, and we're going to add I and 1 just to check if it's even, and that's pretty much it. Let's go ahead and submit our answer just to show that we have a working solution. And we can see that it's faster than 99.96% of previous submissions. So that's about it for another question of the Blind 75 challenge. Come back tomorrow, we're going to continue on with some more binary, and we're almost to the end of this section. And one more thing, if you're enjoying this series, don't forget to click like and then hit that subscribe button. I'd really appreciate it. Thanks guys, and I'll see you again tomorrow for another question.